Imagine soil suddenly losing all internal friction. Liquefaction is the temporary loss of shear strength in saturated, cohesionless soil triggered by seismic loading. This phenomenon initiates when cyclic shear strains from earthquake waves cause a rapid, undrained increase in pore water pressure. The effective stress, defined as the total stress minus the pore water pressure, consequently approaches zero. This elimination of effective stress removes the frictional resistance between individual soil particles. When effective stress reaches zero, the soil mass transitions into a state behaving like a heavy liquid, incapable of supporting static loads. This critical state is technically termed initial liquefaction, resulting in zero shear stiffness and catastrophic foundation failure potential. Understanding this effective stress collapse is fundamental to mitigating seismic risk in infrastructure design. Liquefaction primarily targets loose, saturated, granular soils. Specifically, poorly graded sands and silty sands, classified geotechnically as SP or SM, exhibit the highest susceptibility. The soil must be fully saturated, meaning all voids are completely filled with water, typically occurring below the standing groundwater table. Loose packing, characterized by a relative density below 50%, is critical. Under cyclic stress, these loosely packed particles attempt to rearrange and reduce volume. Since water is incompressible, this volume reduction tendency transfers the entire load instantaneously to the pore water. Gravels and dense sands are generally resistant. Gravels possess high permeability, allowing rapid pressure dissipation, while dense sands have high initial effective stress. Clays are immune because their cohesive bonds prevent particle rearrangement, and their low permeability inhibits rapid pore pressure buildup. Under static conditions, the total vertical stress is distributed between the effective stress carried by the soil skeleton and the pore water pressure. Earthquake shaking induces cyclic volume reduction tendencies specifically in loose sand deposits. Because water is nearly incompressible and drainage is inhibited during the rapid shaking event, an undrained condition, this volume reduction tendency directly translates into a rapid increase in excess pore water pressure. As the pore water pressure rises, the effective stress decreases proportionally, directly reducing the contact forces between the individual soil grains. When the effective stress ratio drops significantly, the soil loses its inherent ability to resist shear forces. This loss of resistance leads directly to catastrophic failure modes, including liquefaction flow slides or cyclic mobility failures. The triggering mechanism for liquefaction is the cyclic shear stress induced by propagating seismic waves. Engineers quantify the seismic demand using the cyclic stress ratio, or CSR, calculated empirically from the peak ground acceleration and the overburden stress at depth. The soil's inherent resistance to liquefaction is measured by the cyclic resistance ratio, or CRR. CRR is determined through specialized laboratory tests or established empirical correlations based on standard penetration test end values or cone penetration test tip resistance. Liquefaction is predicted to occur when the CSR exceeds the CRR, resulting in a factor of safety against liquefaction less than 1.0. The duration and magnitude of shaking are crucial variables. Longer duration earthquakes generate a greater number of stress cycles, significantly increasing the likelihood of critical pore pressure buildup. Liquefaction causes three primary failure modes impacting structures and infrastructure. First, bearing capacity failure occurs when the liquefied soil cannot support foundation loads, resulting in excessive differential settlement or severe tilting of buildings. Second, hydrostatic buoyant forces can cause light structures, such as buried utility tanks or pipelines, to float upwards through the liquefied soil mass. Third, lateral spreading involves the downslope movement of large blocks of surface soil riding over the underlying liquefied layer. Lateral spreading frequently causes severe damage to bridges, retaining walls, and critical utility lines. Even slight ground slopes, sometimes as low as 0.5%, can trigger significant lateral displacements, potentially exceeding several meters in severe events. Geotechnical investigations are mandatory in seismically active regions to accurately assess liquefaction potential. The primary field tests utilized are the Cone Penetration Test, CPT, and the Standard Penetration Test, SPT. CPT provides continuous high-resolution data on tip resistance and sleeve friction, which correlates directly to the soil's density and shear resistance. SPT measures the number of hammer blows required to drive a standard sampler, providing an empirical measure of soil stiffness and density. Shear wave velocity measurements are also employed, as lower velocities reliably indicate looser, more susceptible soil conditions. These field data are used in conjunction with established empirical charts, such as the Seed-Idris simplified procedure, to calculate the required factor of safety against liquefaction for design purposes. Mitigation strategies focus on either increasing the soil's inherent resistance, the CRR, or significantly improving drainage capacity. Densification techniques such as vibro-compaction or dynamic compaction increase the relative density of the sand deposit, making it inherently less prone to seismic volume change. Stone columns or aggregate piers are installed to densify the surrounding soil and simultaneously provide high permeability drainage paths. These paths allow excess pressure to dissipate rapidly before liquefaction can fully develop. Chemical grouting involves injecting stabilizing agents into the soil voids, effectively increasing cohesion and stiffness. Deep soil mixing is another technique, blending the susceptible soil with cementitious binders to create a solidified, non-liquefiable matrix capable of supporting structural loads. When ground improvement is either impractical or cost-prohibitive, foundation design must effectively bypass the liquefiable layer. Deep foundations, such as driven piles or drilled shafts, transfer structural loads through the susceptible soil layer down to competent, non-liquefiable strata or bedrock. These deep foundations must be specifically designed to withstand potential downdrag forces resulting from the settlement of the surrounding liquefied soil. Furthermore, they must resist significant lateral loads caused by large-scale lateral spreading movements. For critical infrastructure, performance-based design requires ensuring the structure remains functional even if some minor liquefaction occurs. This often involves utilizing robust, interconnected mat foundations or rigid box structures to minimize damaging differential movement across the structure's footprint.